operator for total energy in terms of differential with respect to time. As we know that the wave function associated with a particle moving along x-axis is psi of x over t, which is equal to a into e raised to the power iota over h bar p of x into x minus e t. Now differentiating with this relation or this equation, differentiating this equation with respect to time, we have partial psi of x over t over partial t is equal to a partial by partial t e raised to the power iota over h bar p of x into x minus et. If we apply this differential operator, we get a into minus iota over h bar e, and then we have iota over h bar e raised to the power iota over h bar, and we have p of x into x minus et. Or we can write this as minus iota over h bar into e, and then we have a e raised to the power iota over h bar p of x into x minus et. Now this is again the same wave function psi of x over t. So partial psi over partial t is equal to minus iota over h bar e, and then we have the same wave function. If we bring this factor to the right hand side, we get iota h bar partial by partial t of psi is equal to e of psi. Now this is an eigenvalue equation where iota h bar partial by partial t is an operator, e is an eigenvalue, and psi is an eigenfunction. So we can write the operator of energy is iota partial by iota h bar partial by partial t. This is the energy operator in terms of differential with respect to time. Now we will calculate the angular momentum operator. As we know that in classical mechanics we define the angular momentum as L is equal to R cross P. Now from this we can calculate the angular momentum, which is R as xi plus yj, the position vector r, plus z into k. Cross momentum is a vector quantity which has three components: p of x I plus p of y into j plus p of z into k. If we do this cross product, we finally get y p of z minus z p of y into I plus z into p of x minus x into p of z into j plus x into p of y minus y into p of z into, this is x, sorry, here we have x into k. Also we can write angular momentum into its component as Lx into I plus Ly into j plus Lz into k. If we compare these two equations, then this represents the x component of angular momentum, this represents the y component of angular momentum, and this represent the z component of angular momentum. So the x component of angular momentum is Lx is equal to y p of z minus z p of y. And the y component of angular momentum is z p of x minus x p of z, and the z component of angular momentum is x p of y minus y p of z, p of x, sorry. Now if we write these in terms of operator notation, then Lx is equal to y operator p of z operator minus z operator p of y operator. Similarly, Ly operator is z p of x operator minus x p of z operator, and L of z is equal to x p of y operator minus y p of x operator. Now operator of position is the position itself, operator of y is equal to y, and z operator is equal to z, and p of x is equal to minus iota h bar partial by partial x, p of y operator is minus iota h bar partial by partial y, and p of z is equal to minus iota h bar partial by partial z. Using these values in these three equations, we get the operator of angular momentum along x direction is minus iota h bar y partial by partial z minus z partial by partial y. Similarly, the operator of momentum along y axis is minus iota h bar z partial by partial x minus x partial by partial y, and Lz operator is minus iota h bar x partial by partial x y minus y partial by partial x. So these are the operator for momentum. Here I just put p of x, p of z by replace p of z operator by this, and p of y by this, and I will do one of them, which is Lx is equal to y operator is y itself, and p of z is minus iota h bar partial by partial z, and then minus z operator is z itself, and then p of y is minus iota h bar partial by partial y. Now minus iota h bar and minus iota h bar, they are common here, so we can keep it take it common, minus iota h bar. Here we left with y partial by partial z minus z partial by partial y. So Lx is equal to minus iota h bar y partial by partial z minus z partial by partial y. So this is this one. Similarly, if we put these values in this relation, we get this one. If we put this value in this relation, we get this one. So these are the operator of momentum and x, y and z direction. This is all about operator of physical quantities. In the next videos we will discuss few problems, and then we will move to the Schrodinger equation. Thank you.